Good morning, everyone. I'm excited to welcome you to today's presentation. We will be exploring the fascinating topic of the kernel concept in operating systems. My name is Subhasree Maity, and I am an assistant professor in the Department of Computer Science and Engineering at Swami Vivekananda Institute of Science and Technology. Over the next few minutes, we'll look at what a kernel is, how it functions within an operating system, and why it's so crucial for computer performance. Let's get started. So, what exactly is a kernel? Well, the kernel is really the core part of the operating system. It's responsible for managing all the system resources. Think of it as the control center that keeps everything running smoothly. It also handles communication between the hardware, like your CPU, memory, and devices, and the software applications you use every day. In a way, you can think of the kernel as a bridge, connecting applications to the hardware layer, ensuring they work together seamlessly. Its main responsibilities include managing processes, which means overseeing how programs run and share resources. It also takes care of memory management, making sure each application has the memory it needs without interfering with others. And of course, it manages devices, everything from your keyboard and mouse to printers and storage devices. Understanding the kernel is fundamental because it underpins how the entire operating system functions, allowing us to run multiple applications efficiently and reliably. It's truly the heart of the system, coordinating all these activities behind the scenes. Now, let's take a closer look at the main functions of the kernel. First up is process management. This is where the kernel handles creating, scheduling, and terminating processes, ensuring that each task gets the resources it needs while maintaining system stability. Next, we have memory management, which involves efficiently allocating and freeing memory so that processes can run smoothly without interfering with each other. Moving on to file system management, the kernel organizes data storage, allowing us to read, write, and manage files seamlessly across different storage devices. Device management is another crucial function. It ensures proper communication between the hardware devices and the software, managing inputs and outputs effectively. Then, there are system calls and interrupt handling, which form the bridge between user programs and kernel services, while also allowing the system to respond promptly to events like hardware signals. I/O communication is essential for smooth data exchange between peripherals and the system, maintaining efficient operation. Lastly, security and access control are vital to protect the system from unauthorized access and ensure data integrity. Overall, these functions work together to make the operating system reliable, efficient, and secure, supporting all the other components and activities we've discussed today. Let's take a closer look at the architecture of the kernel. The kernel essentially acts as a bridge, providing a structured interface between the hardware components and user applications. This means it manages how software interacts with physical devices like disks, memory, and processors. Typically, the architecture is organized into several layers. At the very bottom, we have the hardware layer, which includes all the physical devices. Above that is the kernel layer itself, which handles the core functions like process management, memory management, and device control. Next, we have the system libraries, which offer reusable functions that applications can call upon, simplifying their development and ensuring consistency. Finally, at the top, are the user applications. These are the programs that users interact with daily, relying on the underlying layers to operate smoothly. Understanding this layered structure is crucial because it highlights how the kernel serves as the foundation that ensures stability, security, and efficiency in the entire system. It's the key to how everything from your operating system to your apps works seamlessly together. Let's take a closer look at the different types of kernels. First up is the monolithic kernel, where all the operating system services run directly in kernel space. This means that everything from file management to device control is handled in a single, large kernel, which can be very efficient but also more complex to maintain. Next, we have the microkernel. Here, the core functions are kept minimal, only the essential parts like communication between processes and basic hardware management. The rest of the services, such as drivers and file systems, run in user space. This design aims to improve modularity and stability, as failures in user space services don't crash the entire system. Then there's the hybrid kernel, which is essentially a blend of the two previous types. It combines the efficiency of monolithic kernels with the modularity of microkernels, aiming to get the best of both worlds. Finally, we have the exokernel. This one gives applications more direct control over hardware resources, bypassing many of the traditional abstractions. This allows for highly customized and optimized performance. Think of it as giving applications the keys to the hardware itself. Understanding these different kernel types helps us see how operating systems can be designed to balance performance, modularity, and control, which is fundamental to choosing the right architecture for specific needs. Let's take a closer look at the differences between monolithic and microkernel architectures. In a monolithic system, all the core services are integrated into a single large kernel, which means it's generally very fast because everything operates in kernel mode. However, this design can be less secure because if one part is compromised, it can affect the entire system. On the other hand, microkernels are more modular. They run only the most essential functions in kernel mode, while other services are handled in user space. This approach enhances security and makes the system more flexible, but it can sometimes lead to slower performance due to the additional communication between modules. For example, Linux and Unix are classic examples of monolithic kernels, where everything is tightly integrated. Meanwhile, microkernel-based systems include Mach, Minix, and QNX, which separate services into distinct modules. As we see, choosing between these architectures depends on the specific needs for speed versus security and modularity, which ties back to our overall theme of understanding the fundamentals of operating systems design. Let's talk about system calls and how they relate to kernel mode. System calls are essentially the bridge that allows user applications to request services from the kernel. Think of them as the interface through which user programs communicate with the core of the operating system. Now, operating modes are key here. We have user mode, which is where most applications run, and it has limited access to hardware and system resources. This limitation is crucial for security and stability. Then there's kernel mode, which grants full access to hardware resources, enabling the kernel to perform critical tasks. The kernel is responsible for managing these modes and switches between them as needed. For example, when a user application needs to perform a sensitive operation, the system switches from user mode to kernel mode. This mode switching ensures that operations requiring full hardware access are handled securely and efficiently, maintaining the overall integrity of the system. Connecting this to our overall theme, understanding these modes, and how system calls facilitate communication is fundamental to grasping how operating systems manage resources and secure operations. All right, let's take a closer look at kernel space versus user space. Kernel space is essentially where the core of the operating system runs. This includes critical functions like managing hardware, memory, and system resources. Because it handles such sensitive operations, it needs to operate with high privileges. On the other hand, user space is where applications and user programs run. Think of it as the environment where your everyday apps, like your web browser or text editor, operate without direct access to the core system functions. Now, switching between these two spaces, kernel and user, is vital for system security and stability. This transition acts as a safeguard, ensuring that applications can't directly manipulate the core system, which could lead to crashes or security vulnerabilities. So, in essence, this separation helps keep the system running smoothly and securely, allowing applications to function without risking the integrity of the core OS. It's a fundamental design that supports both stability and security in our computing environment. Let's take a closer look at some modern kernel examples. First up, we have the Windows NT kernel, which uses a hybrid architecture. This means it combines elements of both monolithic and microkernel designs, aiming to balance performance with modularity. Next, the Linux kernel is primarily monolithic, but it supports modularity, allowing us to load and unload features dynamically. This makes it quite flexible and efficient. Moving on, macOS uses the XNU kernel, which is also a hybrid. It combines the Mach microkernel with components from BSD. This hybrid approach helps optimize performance while maintaining certain modular features. And finally, the Android kernel is based on Linux, benefiting from Linux's robustness and widespread support. Seeing these different examples highlights how kernel design can vary depending on the needs of the operating system, but the goal remains the same: to manage hardware and software resources effectively. These variations also reflect the overall theme of adaptability in kernel architecture, which is essential for supporting diverse computing environments today. Let's wrap up with a quick summary. The kernel is truly the heart of the operating system. It's the core component that manages how everything works together behind the scenes. Essentially, it handles communication between the software we use and the hardware that powers our devices. There are different types of kernels, including monolithic, microkernel, hybrid, and exokernel, each with their own design approach and advantages. The kernel's main goal is to ensure that resources like memory and processing power are managed efficiently and securely. This is crucial for the overall stability and performance of the system. So, understanding the kernel helps us see how all these complex parts come together to make our devices work smoothly.